Okay, we're recording now. All right, and then next thing I said, what's the trajectory look like? I get a lot like this. This one, I forget who that is. Who's that? Is that
Maybe that's...
Nadia? Okay. And then I get George. You gave me both. Can you put both, George?
No, I drew one, and then so it's easier to do this because I have.
Okay, I see.
Drawing it the first time, so I was like, wait, just let me do the straight one first, and then just connect.
All right. So which is the actual trajectory then? The curvy one or the straight one?
The curvy one.
Right. Okay. What is that curve aspect telling us about the way in which he falls?
His acceleration.
Acceleration.
Well, I mean, I think his speed changes. That's what it says.
Yeah, his speed is changing, right? If I start to put dots on here, you can see that if I try and keep them evenly spaced, the dots are falling more and more as I move to the right, okay? So that curvature, because Nadia, you seemed a little bit uncertain about making it curved or straight. Yeah. And the curvature is reflecting the speeding up process, okay? One of the cool things about calculus is you actually know a lot of calculus inside, intuitively. This is one of those TOK moments, right? Because intuitively you can see speed, you can see acceleration, you're used to it all the time. When you cross the street, you have to see the car coming to decide, do you have enough time to make it or not? And so you know a lot about speed and acceleration, which is where calculus comes from. But what we're really trying to do is formalize that, okay? Making that a little bit more close to the way of knowing reason, okay? So we can talk a little bit about that. Anyways, I said, I think my question was, what do the dots tell us about Mr. Skiff's speed? And I get, Ben, this is Ben, I think, right? No, George. George, Ben, and somebody else down here. Who's this? They're Ludovico. You guys take physics, correct?
Yeah.
Yeah, because you told me the physics. It's definitely true.
Sir, all people in this class take physics.
Everyone takes physics. Victoria, do you take physics?
Yep.
Okay, so you guys all know in physics that there's an acceleration due to gravity, and he's jumping, so he's subject to that. But what I was really looking for is, what does the scatter plot tell us about Mr. Skiff's speed? Okay, so if you look at the scatter plot, the dots here tell us something about his speed. Okay, and we got, Vinny said, the scatter plot shows the speed is increasing as the points represent the relationship are getting spaced closer together. Okay. This scatter plot tells us the speed is increasing as he falls. This can be shown by drawing secants for short periods of time, which is what this is what Leo said, which is what we eventually ended up doing. Okay. So this scatter plot is telling us that his speed's increasing over time, because you can see those dots are kind of spreading out as we go down. Yeah? Okay, they're forming a curved shape, right? So I went a little further with this and I asked you guys, what does the average rate of change represent? So I gave you a graph and I said, oh, someone move this one around. And I said, if I take those 2 points and I measure the slope of the secant, that's the average rate of change, okay? And yeah, that's the slope of the secant line. So a little bit of just a moment to talk about communication here. It's not the line, it's the slope of the line. Yeah? Is that clear? Okay, so the average rate of change is the slope of the line. Okay, now, then we said define the average rate of change for his jump. And so I just took a table from somebody here, Nadia, did a nice job on her table. Yes, dear? These are your calculations. They look pretty correct. I think they're right. What do these numbers tell us here? Anybody?
The slope of the secant.
Ludovico, they're the slopes, right?
Yep.
What do they tell us about the slopes?
It increases as it goes.
Yeah, they're getting steeper as they go down. So what does that tell us about the fall? The way in which he's falling? We make the connection with the geometry to the reality.
Like the height is decreasing at an increasing rate.
Yeah. More simply, what's happening to his speed?
Increasing.
Increasing.
Yep, so these changing slopes of secants, the fact that they're getting more and more steep here is letting us know that he's speeding up, okay? All right, so if we, let me get this out of the way here. This thing just always stays in the way. I want to go back here. Okay, and then I said in the next screen to do something a bit different. Here we said, let's find his speed at 1 second. Could someone explain this table? This is kind of key to what we're going to do today. Anyone give a go at that?
That's the difference in the the slope between the slope of the secant.
Isn't that
One
the
point is 1 and the other is 1.1 or 1.01.
Yeah, that's right. Ben, Vicky, you want to add something?
that's the rate of change?
It's both, yeah. It's the rate of change, the average rate of change between two moments in time. Okay, that's the concept. And then as Ben's saying, that's actually the slope of the secant between two different points. Okay, now each of these calculations have one point in common. Which point is that?
1.
Yeah, at 1 second, he was 7 meters above the ground. I can see that right here, right? That's 7. And the other moment in time is just different. It's either at 1.5, 1.1, 1.01. And then we also went from 1.5 a second, 1.9 seconds. Yeah? So this table is completed very well. The next question, which I'll just ask because I want to keep the table on the screen, or maybe we can actually see, hold on. I think we can see the table if we go to your answer. Yeah, how fast was he falling at 1 second? Who's this one here? Did we get the table? Oh no, this is a picture. Nadia, let me back up. Okay, so you said he thought he was going around 9.
Mhm.
9, everyone seems to think 9 meters per second.
But
Back up. Why 9? Can you guys explain that?
It converges at 9 and
Something's
the 2
converging
points
at
will eventually
9,
get
yeah?
so close that they will be 1.
What's that, Ben?
The 2 points will eventually get close enough where their difference is like negligible, and that will just be the tangent of 9.
So this average speed here, you're saying looks like a tangent line. And
Yes.
that's the one that's the best measure of his speed. Is that what you're trying, is that what, did I summarize what you're trying to say
Yes.
well? Ben,
Yes.
that makes sense? Yeah? Okay, would anyone agree with that? Just give me a show of my hands. I can see all you guys now. Would you agree? Yeah? Okay, perfectly. Perfect. Okay. Why do we need to let the time interval be small? Why can't we just go between 1 and 1.5 seconds or between half a second and 1 second?
because it's going to be a big difference in the slope. Or
Well, the slope's not going to be 9. You're absolutely right there. You can see that when we were at half a second, here it's negative 6.75. This one kind of got cut off. I make it bigger. It's negative 11.24. Okay, so that's right. But what does that mean about the speed? Why can't we just do between 1 and 1.5 seconds? Why do we have to make that time difference to be as small as possible?
Because we know that the speed is changing.
Perfect, Ludovico, right on the money, man. When I drop stuff, that pen goes down. As it falls, it's increasing its speed. Just like when we looked at the average rate of change for the bunny rabbits between those two moments in time where the level of bunny rabbits was the same and we missed the increase and the decrease. When we try and measure the speed of a falling object or any object whose speed's changing, if we try and measure the speed between two moments in time, the problem is at one moment, the speed is different from the other moment. And so since this thing has been speeding up along the way, if we go between two different points, we're not going to get the speed at the actual, say 1 second is here and this is half a second. It's going to be too slow because at half a second, he wasn't going his speed at 1 second. He was going too fast. Okay. And if I look on the other end, if I go between 1 second and 1.5 seconds, yeah, his speed down here was quicker than his speed up here. So I'm going to get an overestimate for his speed. Okay. How does that work out in the geometry? Let me just back up one or back to where we were before and go to the next slide. I think you can see it here. Oh, no, this one doesn't show it to you, right? We're looking for the slope of this tangent line, okay? And you're absolutely right. The best moment is at 1 second. Let me stop sharing this. Oh no, I wanted to keep sharing, excuse me. Share my screen, the desktop. Let me open up a different. There. How's that? Can you guys see this graph?
Yeah.
I played for you today. Okay, let me stop the animation. Can I stop this thing from moving? Yeah. So this is like at 0.9. Can I get it to 1 second? So I'll put this one at 1 and 7. And so what we were doing is we were finding the slopes of these secant lines, and they're pretty close to the slope of the tangent line. Okay, I've drawn that here for you guys in green. But it gets really close when I get close to that point. Yeah, can we zoom in a bit? Yeah, you can see the slope of the secant. It looks really close to the slope of the tangent, but it's a little bit off. Can you see now how it's a little bit different?
Mhm.
It's a little bit too flat. So I'll get closer and closer and closer. And it looks like it's right on, but it's not quite. It's still a little bit different, you see? And this is only going to go up as close to 0.9, I think. I can get this 0.98 or 0.99. I can get it to see there. And then when I go to the next one, 0.99, it's really almost the same as the tangent, but not quite. If I zoom in, I think we can see, there it is. We can see a bit of space between the green and the black, okay? So negative 0.8995 is pretty close to the slope of the tangent, but not quite. Now, if I go to the next step, what happens? Whoa. Do you see that? What happened to the slope of the secant's being measured right in here? What happens when I go to the,
Undefined.
why is it undefined?
So you're dividing by 0.
Perfect.
Yep.
We're dividing by 0. You got a 0 on the top and a 0 on the bottom. So it's undefined. Today, we want to give that some definition. Okay, and that's what the notes are about. Okay, so hopefully that Desmos activity gave you a good feel for how this works out. Is that Leo there?
Yes, I'm sorry.
Okay, and Anthony.
I thought you will send an invitation like 10 minutes before the class.
I thought I did. Didn't I send one to you guys?
No.
Yeah, you sent it yesterday.
What? I
I
didn't
sent it
receive it.
yesterday, I think.
Oh yeah, it was yesterday, but I expected it to have like 10 minutes before the class.
So I think in order for that to happen, you have to somehow get this into your Google Calendar.
Yeah, okay.
Yeah, so I can send them again before, but maybe you guys can just try and keep track of that as well. Okay?
Yes, yeah.
Okay,
I'll do it.
perfect. Okay, that's pretty good. So if we don't have any more questions with that, what I'd like to do with you guys is take a look at the notes that I had given you. Did you guys all get a chance to get those off the Google Classroom?
Yes.
Yeah, if you didn't download them now, so you at least follow along. And I'm going to stop this share, and I'm going to start to share my iPad screen. And you can see together what we're going to do. All right. Are we on? Okay, yeah. Oh, I got to get it right. Okay, so these are the notes we want to look at today. Let me get you guys out of my. It's so hard to work with this thing here. There's my iPad, and I'll give you a big strip there. Oh no, I don't need this. Whatever. Okay, right? So what we're going to do is we're going to look at another display of two moving objects, and I want you guys to tell me what you see. So let me get those out for you. They're on Google Classroom. Okay, moving points. Did you guys take a look at this last night?
Yes.
Okay, I got 2 points, right? The first one is 20t, and the second one is 5t squared. Okay, those are the ones in our note here, see? 20t and 5t squared. And I can't use t in Desmos, so I used a. They're gonna move. I want you to describe the movement. You ready? Watch them again. Chime in. Tell me what you think. What do you see?
One is constant.
Which one's constant, Nadia?
The red one.
So, okay, what do you mean it's constant? It's actually moving. What's so constant about it?
It's not speeding up.
Moving
It's
at the same speed.
Oh yeah,
Yeah.
speed is constant. It's not speeding
No
up.
acceleration.
Which
Zero
you got no
acceleration.
acceleration. Yeah. What about the blue one?
That's
It's accelerating.
With acceleration.
It's speeding up, right?
Yeah.
Is it speeding up? Sure.
Yeah.
Yeah, its speed is changing. Okay, so let's put that in the note, right? Intuition, we don't need math for calculus, it's easy. So a of t, which was here, is constant speed. And B of t is speeding up. Changing speed, whatever you want, okay? So what I did here, down below, is I then, oh, this thing isn't reacting. I then graphed the functions of time on Desmos. And let me just, hold on. It's not moving on me. No technical glitch, come on. Why doesn't it want to do that? Stuck in spot. Okay. Maybe we can look at it this way. Okay, can you guys see that? Is that too small?
Okay.
I don't know why this isn't reacting. It's not reacting to my fingers on the screen. One sec here. Well, maybe I'll set you guys off and then I'll fix it while you're working on it here. So these are the graphs. What you've got to do here, of course, we know that speed is distance over time, right? What I'd like you to do is to measure the speed of A, he's here, and B, okay, between time 0 and time 1. So first second between 0 and 1. And then the next second between 1 and 2, by filling in the chart below. So between 0 and 1, here you want the change in distance, right? So if we're looking at A, you can see right off the graph, how far has it gone?
Yep.
How far?
20.
On to. Wait, I can't see. 20.
That's right. These are 20, okay? And how much time was that?
1 second.
1 second.
Okay, so speed is 20 over 1, which is 20, okay? Can you guys fill in the other bits and try and answer the questions B and C? I gotta just restart this thing so that it'll react. Oh, now it works. What happened? Okay, it fixed itself. I don't know how it did that. We can keep going. Okay. All right, so what about the next moment in time for A? So we got this distance here. How about between 1 and 2 seconds?
20.
How far does it travel?
20.
20.
20.
And time is
So 1 second.
1. Hey, look at it. How is that consistent with what you told me?
Same speed.
Constant speed, okay. Now you said B had increasing speed, so let's try and measure that. So I'm gonna change colors to blue. So now between 0 and 1 second, I can't read that off the graph. Can anyone?
5.
Yeah, that's 5, right? Because remember this B of t function is 5t squared. So 5 units in 1 second, it's 5 meters per second. Should we just say the units are meters per second? Doesn't really matter to us, okay? Okay, what about the next moment in time between 1 and 2?
15.
So B of 1 is 5. B of 2 would have been 20, right?
Mhm.
Yeah.
So 15 is the change in distance over 1 second, and that's 15 meters per second. Okay, why are this, and that's what you were saying, that this blue thing was speeding up, okay? So why are the speeds the same for A? What is it about A's equation?
It's a straight line.
There's no square, like it's a linear equation.
It's a linear equation, right? It's a straight line. So as time increases, the distance increases proportionally. For every second, this one is traveling 20 units. Whereas B, the speeds are different. Because it's Y. Obviously, why are the speeds of B different?
The time is being squared.
It's a squared, right? So you can see by the curvature that as time passes, it's going to travel more and more distance, right? We go to the next unit in time. It's kind of like Mr. Skip's fall, okay? Okay, here's the $1 million question for today. Which calculation best describes the speed of B at 1 second? What's the speed at 1 second? 5 or 15 or something else?
Something else.
Who said 10? Ludovico. Why'd you say 10?
Like average.
Oh, so you wanted to average the two?
Well, because it's changing.
Oh, okay. So that was my next question. Why do you want to average?
Because as the speed is changing, like from 0 to 1, that's an average of the speed between 0 and 1. And as it's changing, it cannot be 5.
Okay, so if the speed is changing between 0 and 1, is 5 too slow or too high?
Oh, too slow.
Yeah, this is a little too slow, right? Okay, what about between 1 and 2 seconds?
I think that 15 is too high.
That's too high. Okay, so, you know, Ludovico is a pragmatist. He says, look, one's too high, one's too low, average them, and that should be the speed of about 10. Anybody agree with that? Hands up if you do. Yeah, Anthony and Leo, can you guys turn your video on?
Yeah.
Yeah, so I can see. Did you put your hand up? Does anyone disagree with that? Danny, it looked like you weren't sure.
I don't know.
I don't think
Ben?
it would be exactly 10.
You don't think
No,
it would
no,
be exactly
less
10?
than
No.
10.
No, not exactly 10. Maybe a
I
bit.
think it would be less than 10 because it's increasing at like before it gets there.
8.
Yep.
It's gonna be
Ludovico?
slow. Like
I think it's like 8, like 10 approximately.
Okay, Ludovico was, I don't think you were trying to say it was exactly 10, but you
No,
were
no.
saying one was too slow and one was too high. So 10 is probably closer than both 5 and 15, right? Yeah. But Ben's saying it might not be 10, it might be something else. Okay? Anybody else have any other ideas of how fast this thing is going at 1 second? What's the problem with the 5 and the 15? If we can identify the problem, maybe we can get a better estimate. What's the problem with using these two estimates here? I think Ludovico already said it.
Right.
They're too big.
The range is too big.
Yeah, you got too much time passing, and this poor thing's been speeding up as we've been waiting for the. There's Anthony. Hi, Anthony. How's it going? Can see your face now. Yeah. So what we're going to do is we're going to get a better estimate by doing a limiting process. This is what's called. We got to go to a little bit of mathematical theory first. Okay. So the theory we already know, right? The secant is the line that touches the graph at 2 points. So that's MPQ. And if you want to find the slope of the secant, it's just rise over run. So in this particular case, I'm going to call point P x1 and point Q, I'm going to give it an x coordinate of x2. Okay. And x2 is really x1 plus some distance, let's call it h. Okay. Does that make sense to everybody there? Okay. So if I wanted to find the rise, well, I need to figure out some of these y values. So this one over here would be f of x2 or f of x1 plus h. Yeah, and the one down here would just be f of x1. Okay, so I can find the slope of this secant by just going, look, take f of x2 minus f of x1, x2 over x1. Yeah, does that make sense?
Yep.
Or I could look at this as, instead of x2, I could write it as x1 plus h minus f of x1. And then what would x2 minus h be? Sorry, x2 minus x1. What would that be? What's the difference between these two?
H.
What's the sign above the equal sign?
This?
Yeah, CH, what is it?
Or.
Ah, okay.
Or.
Thank you.
And so, or. Is it coming in clear for you guys, or is it a bit crazy?
No, it's okay.
Great.
It's clear, okay. So the bottom would just be h, right? Because x2 minus x1 would be x1 plus h minus x1, or just h. Okay? So two different formulas that we can use. We're going to kind of focus today on this formula here. Tomorrow, we'll have them kind of both on the page. And what we're going to do is get a better estimate for the speed by filling in the table below. Okay? So Ludovico proposed 10. Ben suggested that maybe 10 was too high. Let's get to the heart of the matter by, okay, our x1 is h, okay? And our x2 will be 1 plus a bit h, okay? And I'm gonna make h be 1, 0.5, 0.1, 0.01, all these values down below here. You with me? Okay, so if h is 1, then the other point is 2. Okay, so here's what we're looking at. This is the point on the graph right there. Okay, if I come over here to the graph, I want to put a point here at 1. And my first thing I'm going to do is go between 1 and 2. Well, we already did this, didn't we? We did it above on the table, right? Let's just write it in here. We'd be looking for f of 2 minus f of 1 all over 1. Now this 1 down here is h. It's not the one on the x-axis. It's representing this distance here, which is 1. Okay, now, remember, we're still dealing with our equation for b, in which case f of x was 5x squared. I mean, we had 5t squared, but we'll turn it to x and y so it looks more like a regular sort of graph. So this is y is 5x squared, this is y, and this is x. Okay, so how do these numbers actually work out? I think f of 2 was 20, right?
Yep.
Yeah? And so this is 5, 10, 15, here's 20. So it was 20 take away 5 over 1 is 15, right? And Ludovico, he said that's way too big, right?
Mhm.
Okay, so let's let the time frame be smaller. Let's let the h be 0.5. So then we'd be looking at 1.5, okay? So we actually want to calculate f of 1.5 minus f of 1 all over the h, which is 0.5. Okay, so to do this, we're going to need a calculator. And I'm not going to put it, well, if I put it on the screen, I don't know. Let's see. I think it's going to get too small, but I'll try. There's my calculator. So
I got 12.5.
is that 1.5?
12.5.
Right
Yeah,
there? So 12.5 take away 5.
No, the overall result is 12.5.
Yeah.
Oh, the whole thing's 12, so it's
12 and a half.
17.5. Yeah? Is that right?
Yeah.
No, it's
Yeah.
11 and a half.
11 and a half. Okay, I want to go by, the whole thing's 12.5. I got you, okay. So 11 and a half minus 5, and the whole thing comes out to be 12.5. Ludovico, how do you feel about that based on what you told me that this was too big? Now I get a smaller number. Does
Yep.
that make sense? Why should this number be smaller? What happened? What didn't happen between 1 and 1.5 seconds?
We
Like-
didn't include those like faster moments.
Yeah,
The
it didn't
moments
include-
with faster speed.
Yeah, it didn't have as much time to speed up. It only had half a second to speed up instead of a whole second. Okay, well, let's go between 1 and 1.1. Okay, so now we have to calculate f of 1.1 minus f of 1 over 0.1, okay? I'm gonna put a couple of numbers up there because I wanna see some of the numbers working out. Okay, how much can I do here? Figure this out. So we need 5 times 1.1 squared.
10 and a half.
Yeah, that's 6.05 minus 5 over 0.1. So if I take 5 away and then I divide by 0.1, did you get 10 and a half? Oh,
Yeah.
I did it wrong. I did minus 2. You're right. It's going to be 1.05. 10 and a half.
Mhm.
Ah, okay. That's a better estimate, right? Because now we're only looking at 0.1 moment in time of speeding up, right? He only had 0.1 of a second to speed up. Well, let's keep going. Let's put 1.01 there. So now we need, I'll let you guys do the calculations. You seem to be fast enough with it, and then I can make this bigger. F of 1.01 minus F of 1 divided by 0.01. Okay. Anybody got a number for that?
10.05.
Ah. Ben, what do you think about this, or Ludovico, now what do you think about this 10 meters per second?
I think Ludovico was right.
It's looking pretty good, Ludovico. The average is actually working out. It doesn't always work out, but it worked out in this case. Well, let's get to the heart. Let's do 1.01. So now we need F of 1.001 minus F of 1 divided by 0.001.
10.005.
Did you do the calculation?
Yes.
Mhm.
Yeah. Or did you just look at the pattern? It looks like we're adding zeros every time, right?
Yeah.
Yeah.
Yeah, okay. All right. What about if the H were negative? What would that mean?
It's gonna
Be
be
going slower.
Yeah, and what would that look like on the graph? If the h is negative, this is my point 1. What would the other point be if it's?
To the located on the left,
Yeah, that's right.
on the right. Yeah.
Yeah, it's going to be at 1 plus a negative 0.05, which is at 0.5. So now we'd be doing f of 0.5 minus f of 1 over 0.5. So we're looking at this bit over here. You're right, that's going to be a little too slow. What are we going to get if we calculate that?
7.5.
7.5?
Mhm.
Cool.
Mr.
Right?
But isn't it divided by negative 0.5?
Yeah, thanks. Ludovico, you're right. The top would be negative. I need a negative on the bottom. Okay? Now, if it's negative 0.1, we're looking at 0.9. What do we get for that speed? 9.5, is that right?
9.5.
Yeah, no, I just guessed. 9.5, yeah, perfect. Okay, and if it's 0.01, now we're looking between 1 and 0.99 of a second.
Oh, 9.05. No.
Anybody have that one?
9.95.
9.95, Ben?
Yes.
Okay, so if you had to guess and you had to give me a number, what would you tell me the speed or the slope of the tangent is at x is 1?
10.
10.
10. Beautiful. Yeah? Wow, that's a lot of work just to
Wait,
get
sir,
a 10,
that's 10
isn't it?
factorial. That's not 10.
No, it's not 10 factorial. It's 10.
No, no, Ben,
10
that's
factorial is
10.
much bigger. We're done with discrete math. No more factorials for a while. Okay, so what did we just do? Well, we found the slope of the secant at the different points. So rather than show you this graph here, I think it would be, well, I think we can probably just do a little quick illustration here. Okay, so what we're doing is, let's get a different color here, blue. So we're finding all of these secants. And the ones that are really close are going to give us the slope of the tangent, which is 10. Okay? And when you're doing this, this is called a limiting process. So we're going to give some notation to it tomorrow. But for today, we're just going to work through it kind of without any notation to go with it. But I don't know about you. This plugging numbers in and saying it's 10 leaves me a little bit feeling like, well, what if it's not 10, right? Is anyone out there from the TOK world doubting this? What if it's 10.00001? Could be, right?
Mm-hmm.
We don't have any evidence to say it's not. We're just going with what's called, I call this the whole number theorem in math, right? Every high school math problem usually has a whole number answer, so the answer should be a whole number. No, that's not a good way to go. We can actually show it's 10 algebraically. And this is kind of what I want you guys to work on tonight. A little bit of tables and a little bit of algebra, okay? There's not a lot of homework tonight, by the way. So this is gonna go probably right to the end. It's quality, not quantity today, okay? So let's do this algebraically. Let's set this thing up. Let's set up the slope of the secant. Okay, and this is gonna be between 1 and 1 plus h, okay? Between 1 and 1 plus h. But we won't stick a value of h in there, okay? What's the best value of h to use?
H.
If you want to get really close to the slope of the tangent, what's a good value for h?
1.00, small number.
But 0 would be the best, right? The problem is if we put 0 in, what happens?
Undefined.
Undefined.
Yeah, you get this the 0 over 0 thing. I don't even know what that means.
Approaching x. Oh, 0. Approaching 0.
Well, we're going to look at what happens as we get close to 0. So let's set up an expression without putting a 0 in there. Let's see. Remember, we're still dealing with our good buddy 5x squared, okay? So what would 1 plus h, f of 1 plus h be? If I take
It'd
1
be
plus
5
h.
times 1 plus h squared
Right. And then f of
minus
1
5.
is just, yeah, right. It'll just be 5. Okay, I didn't make h equal to 0, right? Okay, now's your tricks. What do you do with the algebra now? What would you guys do?
You can expand.
Expand the brackets, okay? So we have 5 1 plus 2h plus h squared minus 5, yeah? Can we put 0 in now?
No.
No, if we put 0 in, we'll get what? 0, 0, we'll get 5, we'll get 0 with 0. Okay, so what should we do next?
Like multiply out the.
Yeah, distribute the 5.
All right, so 5 plus 10h plus 5h squared minus 5. Can we make h equal to 0 now?
No.
No, there's still an h on the bottom, but what can we do instead?
We can like take away, like cancel the h's.
Well, yeah, we cancel a 5.
One h.
And then, okay, one step at a time for the first time through. Yeah, we could cancel an h out, right, Ben? It'll look like we can factor the h out of the top. Okay, and then we can cross out these h's. And then what do we have?
10 plus 5h.
10 plus 5h. Now, you were telling me the best estimate for the speed or the slope of the tangent is to let h get close to 0, right? Here's how we write that. We say let h arrow, let h get close to 0. Okay, if we do that, the dy dx goes to
10.
right? 10 plus 5 times 0, which is 10. Okay? And this is the algebraic way of figuring out the slope of the tangent of the graph y equals 5x squared when x is 1. Make sense, Anthony?
Mm-hmm.
You there, Anthony?
Yeah, sorry, I had to my Wi-Fi cut out for a second.
Okay, good. All right. Okay, so let's try it again. Let's deal with a different function and a different point. X squared at x is 2. Okay, so this is x squared. I think to make this look good, we have to scale this like 1, 2, 1, 4. I want the slope of the tangent right there. Okay. Looks like it, you know, I don't know what it is. We're going to find out.
Mm-hmm.
What's the slope of
2.
what's that?
You want the slope at 2, yeah?
I want the slope of the tangent at x is 2. Okay, so this is my graph y equals x squared. When x is 2, I'm looking for the slope of this tangent right here.
Mm-hmm.
What we're going to do is we're going to set up the table again, and then we'll do it algebraically. One more time with the table because it's pretty instructive. So we want to calculate.
Can we pick the smallest h?
What's that, Leo?
Can we pick just the last two values?
Should we just do it? He says, what do you want to fill all these ones in for? You know these aren't accurate, right? He says the best one is the smallest value of h.
Yeah, but let's do it for practice.
All right, okay, so this is the one he wants to put. Well, wait a minute, which one is it, Leo? The last row, or which row is better? They're
We
the
can
same,
test
right?
both.
Okay, so we'll do
Yeah.
these two, okay? So we're gonna go between 2 and 2.001. Okay, so we have to calculate f of 2.001 minus f of 2, and we're going to divide by 0.1. Anybody can do that on their calculator? Let's see here if I can pull this up for us, yeah? So we got to do, well, it's just in brackets, 2.001 squared minus, the other bit is 4, right? Divided by, I get 4.01. Okay, now on the other side, when the h is a negative 0.001, what's the x2 point going to be right here? What are we going to put in that row?
1.999.
1.99, okay. And so now we have to do f of 1.999 minus f of 2 divided by a negative 0.001.
So 3.39.
Did you do it already?
Yeah, yeah.
3 point, and then like 999,
3 nines. Yeah,
like that. Okay. Can I just check just to be sure?
of course.
Everyone can see it happen. Take away 4. That's a negative on top, and then we're going to divide by a negative 0.001. Yes. So what do you think the slope of the tangent is?
4.
4. Can I, there. I got a circle, so it's not a factorial, Ben. Yeah? Are you guys happy with that? 4? Close enough?
Yeah.
Yeah.
Wait, what if it's like 3.999999999 stock? How do we know for sure? Well, you know how it was. Where's our way of, our TOK timeout up here on the sideboard? Remember, if I did some algebra, you're more convinced, right?
Deductive reasoning.
Okay, this is inductive, isn't it?
Yeah.
All right, let's do the deductive reasoning, okay? So let's find the algebraic approach, okay? So what we're gonna do is set up f of x1 plus h minus f of x1 all over h, okay? So in this particular case, what's the x1 equal to?
X.
2.
It's 2.
That's the 2, right? So it's f of 2 plus h minus f of 2 all over h. Okay. Now's our chance for algebra. 3 cheers for algebra, right? Right, Anthony? How can we work with this algebraically right here? I guess we don't need the calculator anymore because we're going to do the algebra. What's f of 2 plus h going to be?
X plus h.
2 plus h squared.
Yeah, 2 plus h all squared. And then f of 2 is just going to be 4, right?
Mhm.
All over h. Are we ready to make h equal to 0?
No.
No, we got a 0 on the bottom. We don't know how to divide by 0. 0 for 0 is a weird thing. Okay? So what should we do next?
Expand.
Yeah.
4 plus 4h plus h squared minus 4 over h. Yeah?
Yep.
Yeah. 4
And then?
cancels out.
Then you can cancel the 4 and factor the h.
Yeah. And then factor the 4h plus h squared. And then the h goes away.
Yeah, so at this point, what we have here, guys, is this is the slope of the secant. The secant between 2 and 2 plus h. What you're saying is let the h go to 0. Then the slope of the secant is going to go to
4.
4. Perfect. That's the slope of the tangent. Cool. All right, let's see if we can do 2 more examples before we stop for today. I think that's it, right? Okay. And can you guys set up the next one on your own? And I'll come back. While you're doing that, I'm going to put something on the graphing calculator to show you, and then we'll look at the result, okay? So we got about 10 minutes left. See if you can do example 3. Is anyone not sure how to get started? Okay. X is now -1, and the function is 2x squared plus 1. So it's slightly different.
Did you get example 3 as -4?
What'd you get?
-4.
Minus, anybody else get -4? Okay,
Wait, I didn't do it.
let's check it here. So we're looking at,
Yeah.
okay. So we're looking at something like this, right? Okay, so what'd you do next, George?
Oh no, I just wanted to see if it works. I just did something a bit different.
Did you say like 4 times -1?
Yeah.
Yeah. Oh. George knows some secrets. Does anybody else know the secrets?
No.
Okay. He knows some shortcuts. We're going to get to those probably by next week, George. Easy going, right? We want to make sure we understand exactly how that works. So the way we're going to do it is by finding the slope of the secant between -1 plus h and -1 and let that h go to 0. So I get to this point. What's my next step?
Grade
You,
2, h minus 1 squared plus 1.
Yeah, you have to sub those expressions, these,
the equation.
into the equation, okay? So we get 2 -1 plus h squared plus 1 minus, make sure you put this in brackets, 2 times -1 squared plus 1, okay? Good, okay, Ludovico, what's next, sir?
You expand the minus 1 plus h squared.
So what do we get? We get 1 minus 2h plus h squared, right?
Yep.
Oops. Sorry. Plus h squared, then there's a plus 1. And then the thing in the other bracket is 3, isn't it?
Yep.
Okay. Okay, then what?
Then you can expand the 2 with the
Yeah.
h squared minus 2.
So I think we get something like this, right? And then what happens?
1 minus 3.
Because
All the constants cancel out, right? Like if you're like, this is 2 plus 1 is 3, take away 3.
Yeah.
so is what we're doing right now, I think it's called differentiation by the first principle, right?
Yes, sir.
Yeah.
Okay. So I get to this step, and now what?
Cancel out h.
Yeah, you
So
factor
we
out.
get -4 plus 2h. So as h goes to 0, the slope of the secant goes to
-4.
ha. Right, George. You gonna tell us the secret?
I mean,
You're gonna
how
make
to do
us
it?
suffer with this for a little while longer. Suffer. It's better to suffer.
It's up
Okay.
to you, sir.
Can I want to show you guys something a little bit different. I'm going to stop sharing. Your graphing calculator can do this for you. Okay. So if I can share the GDC, let's see how I can do this. Share. Yeah. Okay. So now you should see my graphing calculator. Is that true?
Mhm.
Yeah. You guys see it? Okay.
Yeah.
So you can do this on your examples. You can check these results on your GDC. What I did is I put in the function 2x squared plus 1, and then I graphed it. Now, I changed the window. I'll show you what I did. I went from -4 to 4 just to make it look a little nicer. Otherwise, it's a parabola up at the top. So you're looking for the slope of the tangent at -1, right? That's right here. Okay. So what you're saying, George, -4, does that make sense if you look at this parabola?
Oh,
How come, Anthony? Why ow? Why's your aha moment there?
because it's on the negative side.
It's on negative side, yeah. Okay, let me just do a. I'm going to put a value of the function in there, so it lights up. Enter. Okay, at this point here, what's so -4-ish about the graph? Where's there a negative? What did we just find? -4. What is it?
Slope,
Slope of the
Slope of what?
Slope of the tangent.
the
and
tangent.
Yeah. So if you draw a tangent right in here, that tangent is going to have a slope of -4. That's what you just found, okay? So it's really important, George, if you know the tricks. The tricks we're going to all learn in about a week's time, and they're dead easy, but we have to understand the big ideas behind them, okay? So that -4 is the slope of this tangent. Now, your calculator will do it for you. Watch this. Second function calc. See this one, number 6? dy dx? That's the slope of the
No.
tangent. So you push 6, and the calculator will be waiting for you to tell them an x value. We just did it at x equal to -1, right? Enter. Ah,
Yo.
-4. Okay, so you can always check your answers by second calc 6. All right? Okay, one more before we go, and then you guys can do some next day. I'm going to show you the graph first before we do it. The next example, if you look at your papers, is y equals 1 over x. Yeah? So there's the graph. Oh, wait, let's do a regular. Well, let me just change the window to go -1 to 10. How's that? Okay, so we're looking for the slope of the tangent here at 1. Is that going to be positive or negative, the slope of the tangent right there?
Negative.
Negative.
Okay, let's get it. Let's do, let me share the iPad with you guys again. And let's do this one. Okay, so can you guys see the iPad? All right, so we're looking at f at 1 plus h, because our x is still 1, minus f of 1. All right, go away. Now what?
Oh, you
That's what.
Sub it in.
Okay, so if I sub it in, what do I get?
1 plus.
1 over?
1 over 1 plus h minus 1.
Aha. Now what? There's nothing to FOIL out here. What
Find
would
the
you guys do
common-
now?
Like put
Find
1
common
plus h
denominator.
Yeah, let's get a common denominator in the numerator there.
Yeah.
Okay, so that's 1 plus h, and then the 1 is 1 plus h over 1 plus h, yeah? Okay, now what?
minus h over 1 plus h.
Okay, so this h here, I'm going to write as 1 over h times the numerator, okay? Just because it's getting hard to write. And you're right, Ludovico, we're going to get, or Matteo, you're going to get 1 minus 1 minus h, right? Because it looks like this, actually,
Yeah.
okay? So if we simplify further, what do we get?
H times the
1.
negative.
No.
You'll get a negative h in the numerator, right?
Yeah.
Because this will cancel with that, and then we'll have a negative h. Then what?
You cancel out the h
Yep, cancel out the h's,
and you get
and we have minus 1 over 1 plus h. Can we let the h go to 0 now?
Yes.
Mm,
There's no
Yeah.
more 0 over 0 case. You canceled the 0 over 0 out right there. And you took out the 2 h's. So as h goes to 0, the slope of the secant is going to -1 over 1 plus 0, which is
Oh, -1.
negative
Okay.
1. Well, it's
Sorry.
negative. That's what we said. The tangent should have a negative slope. Yeah?
Mm-hmm.
Can I show you on the graphing calculator? Have we got this down?
Yeah.
yeah, we got it.
You did it already?
Yeah.
I don't know how for you guys to share your screens. I'll figure that out for tomorrow.
Yeah, but we
It's at the
can-
bottom. It says share screen.
Yeah, but then it's hard to see your graphing calculator. I'm just going to put it on here because it's almost time to go anywhere. All right, so if we calc, can you guys see my graphing calculator? Not yet, right?
No.
How's that?
Yeah.
Yeah? Okay, so we're going to calc the derivative at 1. And we get, ooh, wait a sec. Whoa, we're going to end off with a TOK moment. What did the calculator tell me?
Negative
One.
1.00.
What the heck? What's the answer? What's this negative 1.00001 all about? You guys thought I was joking when I said, what if the answer is really like that? Can anyone explain? Well, the calculators give you an approximate value. The algebra is the actual value. So when you get these numbers in the GDC, you have to be a little bit careful with how you interpret them, okay? So the actual answer is -1. all that calculator is doing is finding slopes of secants until they get pretty close to each other. And then he says, boom, that's the answer. So it doesn't do the intelligent stuff that we were doing with the algebra. Okay, so the algebra wins out over it's doing the table method. Any last questions? No? You guys good with that?
Yeah.
Okay, so I gave you like 3 or 4 questions for homework, not a lot.
Okay.
And tomorrow, did we decide, are we meeting tomorrow or not? I can't remember.
I
Mm,
don't think so.
No, it's
There are
right.
office hours.
yeah, office hours.
Office hours tomorrow. Okay, so I'll post a video up because I want to show you the solutions to the homework. Check in with office hours if you're totally stuck. And then there'll be some more of this stuff to work on for Friday. And then Friday's class will pull it back together.
Okay.
Good?
Mm.
Guys,
All right.
All right, guys.
okay, guys. Do we have anything for
Yes,
college counseling today, or we don't?
I don't think so.
Do you
Yes,
have
yes,
chemistry?
we do have college counseling.
Wait,
No,
we
you
have
have to do
college
college counseling?
No.
Yep.
Wait, what?
They're gonna send like a meeting, like call thing, like later today.
Ew, no.
Wait, did they send?
I mean, it said
uh,
on Veracross. I checked Veracross and it said that, well, we're gonna have a college support meeting.
did they
I
say
thought it
that-
was